So good afternoon, everybody. It's a pleasure to be here to talk to you today. I'm going to go straight into it because I've worked with Janie for about a year now, and I know if I don't get on with it, she'll tell me to shut up. So I'll get straight on. So we're changing tact a little bit. We're going to look at end use and particularly propulsion. So what I've actually done is pull together an overview of the propulsion research that we're doing at Nottingham. Over the last couple of years, the amount that we've been doing in maritime has exploded, particularly around alternative fuels. So in terms of the topics, I'll give an overview of what we call the Powertrain Research Centre at Nottingham. Talk about some aligned research programmes with several partners who are here today, and they're aligned to the hub. So we've strategically done that with Tony and others to get the most out of the funding. Talk a little bit about recent results. We've done a lot of work recently comparing retrofit technologies, and there's some interesting observations there. Some new facilities, so Nottingham's investing heavily now in marine propulsion, and then a summary of all of that. Okay. So just very briefly, the group that I look after is called the Powertrain Research Centre. Everything that we do now is looking at decarbonised propulsion systems for heavy transport. And actually, there's a lot of convergence when you look across different heavy applications where you can't use batteries. In green, everything that we're doing now is trying to compromise between having a clean engine and high thermal efficiency. High thermal efficiency means less CO2, but clean covers all of the other regulated and also non-regulated emissions. And when we look at fuels like ammonia and methanol, there are some nasty unregulated emissions we have to think about. We'll come back to that. And the type of equipment that we've got on the left, we've run real single-cylinder engines. So we test fuels in single cylinders. It's cheaper. We've got good access around the engine. That's quite normal practice. And we do that with industry partners. We've got a few engines which have been converted to dual fuel, multi-cylinders. So dual fuel is retrofit to a diesel. And I'll talk a bit more about that. And believe it or not, we still need to take high-speed images of what happens during combustion. We've been using combustion for hundreds of years, but we don't fully understand it with conventional fuels. And when you start looking at things like ammonia that burns really slowly and then chuck some hydrogen in with it, all sorts of wacky things happen. So we also take fundamental measurements as well to try and characterise it. So that's a little bit about what we do. One of the larger projects we've got is what's called MARI NH3. So we've talked a little bit about ammonia. This is a 5-year programme grant funded by the EPSRC, which is taking a holistic overview at how to use ammonia in future marine engines. And being an academic, we can afford to be technology agnostic. So we're approaching this without bias. We want to see what ammonia does, where it sits, how it looks on an acceptance criteria piece. Colleagues touched upon that this morning. There's then some hard engineering. We're looking at fundamentals, combustion, after-treatment. And then how do you actually apply ammonia in real engines, both as a retrofit, but also in future engines? If we're looking longer term, and we've talked a lot about that already, maybe a diesel engine isn't the right sort of engine for ammonia. So that's where we've got to with it all. And we're not doing it alone. We've got some fantastic academic partners that you can see listed across the bottom there. Many of them are here today, so colleagues from Birmingham and Brighton. And we've also got a very active steering group, and I know some of you are here today as well. And when I say active, they are genuinely helping us shape the work that we do. We're not doing this in silos. We're trying to do it for the UK. And actually, if you look at the partners we've got, it's with a UK focus. So, for example, if you look at the engine manufacturers, on the bottom there, Rolls-Royce, they're engine manufacturers who have engineering activity in the UK. That's part of our focus, is to look at what's the opportunity. So that's one of the larger things we're doing. Another thing that we just kicked off, the challenge with marine, you saw some of the facilities there, is scale. So we can go and optimise the combustion on small research engines, but will it scale up when you look at these other fuels? So we've actually just started a new strategic equipment project to commission, top right, a large single cylinder engine, roughly to scale, to be confirmed when it's designed. And that's actually going to be based on a Rolls-Royce MTU 4000, which is used in some of the applications that you can see there in the sort of middle right. And the interesting thing to me when we look at maritime isn't necessarily the large ships. When you're looking at things like ammonia, it's how low a size of ship can you go with ammonia, or should you go in tandem to the safety? So that medium-sized vessel. And actually, when you look at something like that engine, should you electrify it? Should we have 5 engines of different sizes that we can optimise as we vary load? There's all these new possibilities that we can look at with net zero. Okay, so that's just a bit of an overview of some aligned programmes. I now wanted to talk about some real engine test results. So, we're looking at these fuels. Firstly, if we keep retrofit in mind. So if you look on the left-hand side here, what you can see is a cartoon that takes a slice through an engine. So I want you to imagine that we've taken a bandsaw and cut into an engine, and you can see the piston and a diesel fuel injector squirting diesel in orange. That's a normal diesel engine. And actually, we can run it on 100% diesel, just like you would in a normal diesel engine. With dual fuel, which is highly relevant to marine, what we do is we retrofit a second cleaner fuel, and that cleaner fuel is usually a gas, and it's shown in blue. The key point to note is, if you look at the images, these show images of what happens during a single dual fuel combustion event. What you're doing is squirting in about 10% diesel to act like a liquid spark plug, and it ignites the cleaner fuel in multiple places. It's 10% diesel, but if you look in the middle, we've got a lot of orange colour occurring. That's carbon. When carbon combusts, it shows up as orange. So we have reduced the diesel, and you can reduce it up to about 90%. You still need about 10% diesel, but it's still got carbon in it. And we still need, even at high load, up to about 5 to 10% diesel. So the real challenge for dual fuel, with any fuel, let's take natural gas, because that's a really good one. That's a really good fuel from a combustion point of view. But even in a natural gas engine, when you come down in load as the vessel comes into port, the temperatures come down. You're working the engine much less hard, and you end up having to put about 50% diesel back in the engine. So this isn't net zero. It's a short-term strategy to help us start the journey, really, but dual fuel does have its limitations. We've looked at it with ammonia, so we've got a real Volvo D8 engine. I haven't put up any graphs. It's that time in the afternoon, and I didn't want to put up too much data. We've got papers on all of this. Key learning. We can run our engine on up to 90% ammonia. So we can run this diesel engine on up to 90% ammonia. That's been done in the lab. There's an efficiency penalty. You're losing between 5 and 15% efficiency. So an engine that was 40% efficient drops to 25 to 30, which means more fuel. The NOx are up to 50% higher with ammonia. You've pre-mixed the fuel. It carries some nitrogen into the cylinder in the fuel. The real biggie is ammonia slip. And we're seeing numbers that go to the top range of the equipment we use to measure it. 12,000 parts per million is massive. Humans smell it at 5 parts per million. The work exposure limit, so in our labs, our alarms go off at 25 parts per million. So if that exhaust leaks in an engine room, you're in trouble. Now, there is after-treatment technologies that we can throw at it. If we want to use conventional after-treatment, we have to back down the amount of ammonia to about 30%. It's not 90%. Just because you can run 90% doesn't mean you should if you're retrofitting it. So as a group, we became a little bit sceptical at that point, and we changed our focus, actually, of the research that we're doing to spark ignition. So actually, gasoline engines are spark ignited. You have a spark plug in the middle, and you get a pre-mixed flame. It's cleaner, slightly less efficient normally. What we are doing with our partner Marla Powertrain, they've supplied the research engine that you can see on the screen there. The cartoon shows a slice through that engine, and the arrows show the fluids that we can introduce into this test engine. And it's a bit like a flute, because we can chuck all sorts of combinations of fuels in. So as an engineer, it's fantastic. We can play games with all sorts. So what you can see is we've got gaseous hydrogen and ammonia, and we can change the split. We can dial in whatever amount of those we want. We've got a spark-ignited combustion chamber in the middle, and we can squirt in a bit of gasoline as well, if we want. And we've tried, I think it's fair to say, every combination with those. Some headline results. We can run that engine on 100% ammonia, so you can fully decarbonise it, from about a third load up. So when you're coming out of port, we can get it onto 100% ammonia, no problem. And that's what's shown on the right-hand side of the graph. Where it says 100% NH3 on the x-axis, we're running 100% ammonia. The slip is still high. We're getting 8,000 parts per million. So it's about half what we saw in the dual fuel engine. What we've done at constant speed and load is co-fueled the engine with some cracked hydrogen. If you're carrying ammonia, you can theoretically crack a little bit of hydrogen out of it. And what I say when I show this result is a little bit of hydrogen goes a long way. Because if you look from right to left, adding 20% hydrogen, so coming down to 80% on the x-axis, has halved the ammonia slip. So it's really encouraging that. So we've actually changed our strategy of what we're doing at Nottingham with our partners, and also at Birmingham. We're working together collaboratively. And what you can see on the screen is a simple illustration of our strategy. We have a lean burn engine that uses cracked hydrogen with ammonia, 20 to 30%. The yellow bits in the middle, an SCR catalyst is diesel technology. We normally squirt ammonia into that. It's called AdBlue. If you're slipping some ammonia, you don't need any AdBlue. You just need to get the balance right. And at the moment, we've got a new system called an ammonia cracker, which you can use recovered waste heat to crack the hydrogen. And one of our partners is here today, AFC Energy. As of last week, that was up and running on a real engine, and we've got some very promising initial results with that. We're all quite excited about it. So Janie's looking at me. I need to speed up a little bit. Last thing to say, spark ignition doesn't work in big engines. If you go up to a really big bore size, it won't burn. So we're looking at Formula One-like technology and transferring that across to large bore marine engines. And on the screen is just one example. It's called Marla Jet Ignition. We're working with our industry partner Marla. What this is on the cartoon, the orange bit is like a mini combustion chamber. It's called a pre-chamber. And what we actually do is squirt some hydrogen directly into that combustion chamber and run almost pure hydrogen in it. And then there's some little holes at the bottom of the orange area where you see these clouds coming out. They're clouds of really highly reactive species that have been cracked internally from the hydrogen. And this is really encouraging as well, because we need as little as 1% hydrogen to burn the ammonia. Not 20 or 30%, 1%. So it reduces the demand on the cracker. So there's some interesting stuff that we've still got to do there. Last but not least, because of all the work that we're doing on marine, we're actually commissioning a new facility now at Nottingham. And it's going to be a megawatt scale propulsion lab that lets us run hydrogen, ammonia and methanol. So up to 5 megawatts with all the hardware in the loop. That'll let us do things like digital twinning and look at these other fuels with electrification. So again, lots of activity around marine. It's fantastic, I have to say. So to summarise all of that, we're highly active in the space. We're expanding our facilities because of that. It's not just me. There's a large team at Nottingham that are working in this area. And we're very active in cracking. And the plan is to feed all of this data into the marine hub and also to look at methanol in a direct comparison. So that's it from me, Janie.
Thank you, Al.
No problem.